So we talked about flash droughts in the previous podcast, and I've talked about flash floods in this series under new findings in climate change. That's just a generic name I gave since we are talking about climate change in this course. And this paper is slightly different. It talks about threat of low frequency, high intensity floods to global cropland and crop yields. So, as opposed to flash droughts, which are high intensity floods that grow very rapidly, that come upon you very fast. What is low frequency, high intensity flood? So, we'll look at this here. Floods sorry, this is a very long paper with a lot of figures, including the total number of figures is over 30, maybe 30, close to 40, including supplementary figures, which is very unusual for a paper. But nonetheless, flood hazards pose a significant threat to agricultural production. Agricultural adaptation tends to be prevalent and systematic in high frequency flood areas, HFF, but neglected in low frequency flood areas, because if you have high frequency floods, it might come anytime, so you take precautions and make systematic adaptation measures, response measures. Here we, using satellite imagery, we map global spatial distributions of low frequency and high frequency floods at 250 meter resolution for 3,427 flood events between 2000 and 2021. So significant resolution in terms of the scale and large number of events in terms of the sample. We show that LFF affected a larger portion of cropland areas, 4.7%, than high frequency floods, which was at 1.2%. So low frequency, high intensity floods have been more damaging to croplands, and HFF occurred in smaller regions with less intensity. So duration, frequency, intensity and scale are what we worry about in terms of how large they are in scale, how often they are, how long they last, and how intense they are, and so on. Cropland expansion between 2000 and 2019 increased the area affected by LFF to 3.1 times 10 to the 4 kilometers squared, more than that affected by HFF, which was at 1.3 times 10 to the 4, so almost one third. Moreover, the mean yield losses of wheat and rice from LFF were greater than those from HFF, owing to the higher precipitation anomalies, soil moisture anomalies, and greater crop flooding during their growing seasons. Our findings highlight the urgency of this issue and identify priority areas to prevent these neglected low frequency but high impact floods, providing valuable information for developing flood adapted policy. So if you have high frequency and you build a response system for it, but they are not having as much impact as low frequency events, then you have to be careful that you are not missing out the less often but more impactful floods, right? So read off some text. Again, I'm very brief, long paper. I'm going to cut it short. Just give you a summary enough for you to get the main points, but you have to go back and read the paper if you want more details. Floods affect agricultural production widely across the world, although numerous studies have reported the impacts of drought and heat stress on global crop yields. The impacts of floods have been less studied because most current crop models are not well developed in representing the impact processes of flooding and excess moisture. Flooding poses a significant threat to global agricultural production, and this threat may increase as floods are projected to become more frequent and severe in many breadbasket regions under future climate change. Flooding frequency varies, so I'm just jumping ahead. Flooding frequency varies by region. We categorize these events into low frequency floods and high frequency floods according to annual flooding frequency. So there is often a flooding season, unless it's an unseasonal rain and that produced a flood. We defined an area as an LFF or HFF area if the frequency of flood event occurrence was less than 0.5 or greater than equal to 0.55. So less than 0.5 for LFF, greater than equal to 0.5 for HFF within a 6-year window, which is given in these supplementary figures. Compared with HFF, LFF are usually linked to extreme precipitation events with a lowered inundation frequency, larger precipitation anomalies, and higher flood intensity. Global cropland areas have continuously been expanded, but the dynamics of cropland exposed to flooding have rarely been quantified. It's generally believed that floods cause severe crop losses in HFF areas but less in LFF areas. People have just imagined this without looking at data. However, several regional studies have documented higher crop yields in flood-prone areas, and floods were more destructive in arid areas than in wet areas. We already talked about flash floods, where dry regions are now getting more flash floods. Differing outcomes in LFF and HFF for crop yields, including effects on nutrient deposition and soil moisture replenishing, need to be further investigated at a global scale to develop adaptations to changing floods. Okay, so we'll just look at figures as results: frequency, duration, and area of cropland exposed to floods. So they generated 250-meter resolution maps for a large number of flood events over the period. Accuracy of flood maps were evaluated, and indicates that their approach overestimates flooding extent at high latitudes, mainly because of low reflectance objects similar to water bodies caused by low solar angles. So when you rely on remotely sensed data and you are interpreting surface land use as water logging, then you have these problems of interpretation. We therefore kept the related flooding areas with a duration of greater than equal to 4 days for 306 flooding events for latitudes greater than 45 degrees because of their higher accuracy. The overall accuracy of flood detection is 0.78, which is very nice, with a commission error of 0.26 and an omission error of 0.21. So what you include and what you leave out can have some impact on your count as a whole, right? So the details of 2 typical flood events are presented in supplementary figures. Compared with the previous study, we improved flood detection as follows: mapping of additional flood events, distinguishing LFF from HFF, redefining flood duration dates, so the earliest to the latest date of water bodies observed by satellites during the event, and correcting the accuracy of flood maps at high latitudes. Such resolutions, 250 meter, are very critical for doing this, and fortunately such data is available, but you have to go back and look at algorithms, problems like detection that we mentioned, and so on and so forth. So here the frequency of high frequency floods, you can see the regions throughout Europe, North and South America. India, Pakistan, and this region, South Asia, is a hotspot just in terms of the area with the colors. And if you look at HFF, there are also HFFs in this area. So these regions of monsoons are getting low frequency and high frequency floods, and similarly East African and West African monsoons are doing the same. You have drier background climates in the Mediterranean, but you can see that they also have LFF and HFF. This higher frequency of HFF than low FF. If you look at LFF level versus HFF level and durations, here frequency, so you can be sure that what you are looking at. So the scales are going towards increasing LFF level and increasing HFF level in reddish colors, LFF levels in bluish colors, and duration going from reddish to purplish or mixed red blue colors here, and similarly HFF going up, LFF going up, and frequency going up. So it's a mix. So latitudinal distribution of LFF and HFF, frequency of LFF and HFF for different regions. So you can see the range, frequency, and the uncertainties. Latitudes for duration and for duration days for continents. I'm not going into details because I want to focus on the message of the fact that LFF, high intensity LFF floods are doing more damage to croplands and there are regional specific signals in these, and of course that will be season specific as well. So early warnings will have to take care of all of those. Okay. Here is a map of patterns of cropland exposed to flooding from 2000 to 2021. This is for HFF, again HFF going up this way, LFF going up this way, affected area increasing this way. So it's a kind of a difficult map to read in that sense. So you can have duration, intensity, frequency and scale all changing. So how do you want to project it? It's tricky, but they have found a way to do it. So you use it as carefully as possible. Again, there are latitudinal dependencies, and you can see that tropics have certain frequency and intensity or affected scale, affected area, which shows up here in terms of continental. So South Asia, Australia, Africa and so on and so forth. Okay, so this one should help. Affected area in 10 to the 4 square kilometers. Bangladesh is here in terms of total area, and Vietnam, Myanmar, Thailand, Cambodia, so they are in the lower range of total area, but affected areas are larger, whereas Argentina has larger total area but affected areas are smaller. Canada is down here. India is way up here with high total area and high affected area, which is clear in these maps that we have already looked at. United States is here with both high total area and affected area, Russia, China and so on. So if you look at affected area versus total area, you can see the size of the circles that are shown here. It matters because Pakistan is a relatively small country, let's say compared to India, and if it gets heavily flooded, sometimes the entire nation is underwater. So these can matter really, how things are changing and what has been happening already. This is a figure again showing changes in flood affected cropland area due to global cropland change. So you have background intensity, duration, frequency, scale of floods changing, and you have croplands themselves changing as well. So you have to worry about those. So you can start these here again, similarly increasing level, decreasing level with for low frequency floods, and decreasing and increasing levels for high frequency floods with the latitudinal distribution. You can compare to see which ones are changing which way. Are frequencies of LFF and HFF are changing in different latitude bands versus cropland areas, because this will depend on not just floods but how much cropland is there and how the croplands themselves are changing in terms of increasing versus decreasing. So you can see that here is in this latitude band there is much more increase in cropland area than decrease if you take the average, whereas in these regions there is neither a decrease nor an increase. Okay, and we said at higher latitudes there are issues, so they had to do some adjustments for the data as well. And this is for HFF. So this is LFF and HFF. So you can see that the distributions in terms of changing areas, increase, decrease, are also different latitudinally for HFF. So both HFF and LFF have higher signal at these latitude bands. You have to, unfortunately they don't put any tick marks in the middle, which makes it hard to interpret. At least they could have indicated where the equator is, because this is not symmetric. This is 60 south to 85 north. Graphical issues. Okay, so if you look at the affected area for LFF and HFF, again in terms of 100 square kilometers, there are regions where increases have happened, there are regions where decreases have happened. So more decrease here than increase in Tanzania and Mexico, whereas India has seen much more increased affected area in low frequency floods than decreased areas, and USA, China here, whereas HFF, India has still seen some increases, but the difference is, increase is smaller, difference is smaller, but you have to be careful because the scales are different here. This is this is 10 to the 3 kilometers squared, and this is 10 to the 2 kilometers squared. So this is again makes it difficult to compare these two graphs here, but you can see here different periods being considered: 2000 to 2003, 2004 7, 2008 11, 2012 15, and 16 to 19. Okay, so lots of details. If you keep doing this, you will get a lot of figures, which is what has happened in this paper, with tremendous number of supplementary figures as well. Could they have condensed the results better? Well, authors and the reviewers decided this is the way to do it, so we have to use it as best as we can. So here are the LFF and HFF global region statistic: 31 decrease, 69% increase. So you are basically increasing your exposure to low frequency floods as well, because the increase and decrease are similar here, whereas there is a much more increase here. So cropland gain from other is 43%, cropland gain from trees, and cropland gain from wetland and vegetation. So there are land use changes, and which kind of land gets converted also can affect the flash floods, the low frequency and high frequency floods. So cropland gain from trees and from wetland and vegetation for HFF and for LFF. Okay, lots of information, but I am being deliberately brief because it's just data and its interpretation, and essentially we would want to focus on the map of risks from low frequency and high frequency floods, and prepare monitoring and evaluation as well as early warnings, so predictions, right? That would be my goal. So the areas in LFF and HFF areas, MYA are calculated using 5-year running mean based on samples with flooding area greater than 7.5% of the total cropland area. So mean yield, so that's the yield data with the same box plot components as those in figure 1. You can go back and look at. So these are the box and whisker plots, and you can see negative numbers here. So these are basically low frequency floods and high frequency floods. So more losses here, this is for wheat, and more losses here, this is for rice. Slight difference, but still it's important enough to see that the range is large, but even the median and percentiles are large for or negative for LFF. The main message is LFF is being probably not considered as carefully as they should, because maybe high frequency floods are getting more attention and people are getting used to them and protecting against them, but not considering carefully enough the low frequency floods. So here are some more data in terms of mean annual yield differences for LFF and HFF for wheat and rice. Okay, so drivers of yield losses. So this is more important in LFF and HFF. The relationship between global floods and crop phenology has rarely been investigated. The DFO records from 2000 to 2021 show latitudinal heterogeneity in the months when global floods begin and end. So supplementary figure 30, lots of figures. Floods occur mainly in June to August at mid latitudes, and in January to February at low latitudes. These differences are associated with the seasonality of precipitation along latitudinal zones. So obviously this is not the monsoon zone. The significance of the associations between flood timing and vegetation phenology has been highlighted. Since crop phenology is not available in the DFO data, we used phenological data derived from satellite images to identify crop growth stages during inundation periods at the pixel scale. Obviously they have done a tremendous amount of work to extract useful information from satellite data and filling the gaps in the past data as well. We found that precipitation and soil moisture anomalies were more significant in the low frequency floods than for high frequency floods with high significance, especially for SMA, the region. I should be more careful there, but please go back and look up which region corresponds to SMA. I should be able to guess it, but I read it, I should remember it, but obviously skipping my mind, but please go back and look. Floods were mainly associated with soil saturation status and significantly correlated with soil moisture. Using most data products and different methods, we confirmed that the global average precipitation and soil moisture during flood events in LFF areas are significantly higher than those in HFF areas, although there is a possibility of severe flood events due to extreme climate in HFF areas as well. So here is more data on wheat for LFF and HFF in terms of start of flooding. Wow, lots of data that I am not going to go into. Okay, so let's just jump ahead. Relationship between inundation period and crop phenology. So they are extracting more details. It's not just a low frequency, high frequency flood, when they start, when they end, and how the flood period, it's not like the whole period is flooded, but there is a start of a flood season, end of a flood season, and there's start of flooding and end of flooding, and you have crop season. Obviously floods tend to coincide with rainfall season, and floods occur in the rainfall season, and the phenology of vegetation and crops are looked at here again for wheat and rice for LFF and HFF. Okay, this is the wheat area precipitation anomalies in millimeters. You can see how the two types of floods are systematically different, and it's consistent with the total message that LFF is affecting the croplands more. It has to obviously show up in the precipitation, and it does here. Okay, PASMA precipitation and soil moisture anomalies during flooding and crop growth anomalies after flooding. Some more information there, statistical significance, etc. are shown. So let's jump to the summary plot. I'm being tremendously brief because I found this paper to be so detailed that usually you would want to focus your message a bit more. So anyway, let's not criticize the paper, it's useful, so let's just do the best. I'm being lazy basically, so you have to go back and read. Different crop yield impacts from low frequency and high frequency floods. The mechanisms underlying the disparities in crop yield impacts from LFF and HFF. The blue arrows indicate connections among the frequency of precipitation events triggering floods, the frequency of flooding events, and management adaptation for floods. The red arrows indicate connections among the frequency of precipitation events triggering floods, PASMA, and negative anomalies in crop growth. The green arrows indicate connections among management adaptation for floods, percentage of crops in GS during flood events, and negative anomalies in growing season versus crop growth. And the gray arrows indicate the final impact on yield loss. Arrow width corresponds to the effect of magnitude. So lots of information. LFF areas, shorter flood duration, higher intensity. So percentage of crops in the growing season during flood events. Okay, so you have a loop here. The percentage area is higher. Negative anomalies in crop growth. So you are coming from precipitation and SMA anomalies. The lower frequency of precipitation events triggering floods is higher. So not coming through the anomalies. Whereas if it is lower, then frequency of flooding events is weaker. Management adaptation for floods is larger. So obviously you have frequency of floods being low, intensity being high, so you have to worry about whether frequency of precipitation events triggering floods are lower or higher, and the same thing in the higher frequency of precipitation events triggering floods. So you are going here now, higher frequency of flooding events is stronger, management adaptation for floods tends to be smaller, so percentage of crops in GS during flood events and flood of longer duration as opposed to shorter duration here. So if you have lower precipitation precipitation events triggering floods, translating to soil moisture, etc., leading to lower negative anomalies in crop growth. Also, you have percentage of crops in growing seasons during flood events being lower. Brr. I hope it's obvious. Let's just read the discussion. The impacts of floods on crop yield are determined by factors such as crop phenology and flood intensity, which can be reflected by crop growth status. PA and SMA can directly reflect flood intensity. Our results reveal a significant positive correlation where area is smaller to that at the global scale. We used, so there is a parenthesis missing here, we used a unified threshold to classify LFF and HFF globally for comparisons across different regions worldwide in the study. Owing to specific agricultural climate conditions in each region, flood frequency might be relative. So when you say low frequency and high frequency, it's with respect to the local frequency of the climatological frequency. We further analyze the impact of floods on crop yield when using different thresholds to define LFF and HFF in agricultural zones. We found that even with different thresholds, the mean global crop yield losses remain higher in LFF areas than in HFF areas, which is the most robust message that is made clearly here, and the results are similar in different sensitivity tests. Consistent conclusions were also drawn from the influencing factors analysis. In some, flooding processes from initial precipitation to final yield losses are complex and controlled by multi-factor interactions, which are illustrated separately for LFF and HFF in figure 6 that we looked at. In LFF areas, the frequency of precipitation events that trigger flooding is lower, and farmers often have less flood risk prevention and rarely adapt measures such as capacity building for preventing floods, planting flood tolerant crop varieties, or adjusting sowing dates to reduce flood damage. They just think of lower frequency floods as less threatening, I suppose. In LFF systems, a larger proportion of crops is grown with high exposure to flooding, so exposure itself is different. Furthermore, high PA-SMA in these LFF areas cause larger damage to crops in their GS growing season, resulting in larger yield losses. In contrast, in HFF areas, heavy precipitation events trigger floods more frequently, and farmers have often implemented various measures to cope, including drainage systems, changing planting dates to avoid flooding periods, or using flood-tolerant varieties. Moreover, frequent floods generally bring mineral-rich salt to cropland, and together with smaller PA-SMA, on average cause smaller crop yield losses in HFF areas. Our study provides insights into the mechanisms underlying the different impacts from LFF and HFF. Okay, so I hope the message is clear. We compiled an initial global database of LFF and HFF, including these 3,427 flooding events from 2000 to 2021, and this is all about the methodology. We found that the mean duration of HFF was longer than that of LFF for all flood events globally, while the area affected and global mean yield losses from LFF were higher than those from HFF. Make sure you resolve all those things in mind. The flood itself may be low frequency in the sense it occurs less frequently, but its duration is also shorter as opposed to higher frequency flood, which occurs more frequently and its duration is longer. Okay, now maybe that's why farmers don't worry too much about it, because it happens infrequently and it doesn't last as long. Compared with previous studies focusing on exposure, risk, or vulnerability of crops to floods, this study broadens the perspective, discovers the mechanisms, underscores the urgent need, and identifies priorities to prevent losses from low frequency but high impact flood hazards. Some limitations exist in the study. One is uncertainty from the standard thresholds for identifying water bodies in the floods and so on. So just let me jump ahead. You can read the caveats, they are important. Our findings highlight that adaptation measures should be developed to target low frequency but high impact flood hazards. providing timely and valuable information for strengthening and developing flood adapted management measures to cope with increasing flood risk under future climate change. A combination of empirical inferences, process-based models, and satellite observations should be applied to deepen the understanding of extreme climate impacts on agriculture. And there is the issue of predictions, predictability, and early warnings on how to manage these LFF and HFF floods and protect the croplands with appropriate adaptation measures, as they have done for the HFF in terms of drainage, drought, flood resilient varieties, and so on, or changing the cropping dates and so on. Low frequency events may make it more difficult anyway, so we have to see. So I'll leave it here. It's a bit long and I've been brief still, and I've been very miserly or careless in describing the figures, but the main results are obvious, I hope. Okay, see you in the next topic, which should be agroforest. No, I'm in the wrong place. Forest carbon sink. Yeah, maybe. I don't know what the next topic will be. See you anyway.